Welcome to Chapter 5 of the NIMO Introduction series, where we explore advanced topics and next steps. In this final chapter, we'll learn how to extend NIMO for real-world applications. We'll cover custom robot integration using the combat interface, multi-objective optimization for complex materials problems, handling real-world constraints, and resources for continued learning. By the end of this chapter, you'll be ready to apply NIMO to your own experimental systems. NIMO's combat interface, which stands for custom robot, allows you to connect your own experimental systems to the optimization framework. The architecture uses file-based communication, making it universally compatible with any robot system. The workflow has 4 steps. First, NIMO writes proposals, CSV with AA-selected candidates. Second, your custom script reads these proposals and controls your robot. Third, after experiments complete, your script writes robot output, CSV with the results. Finally, NIMO reads the results and updates the optimization. This simple file exchange means you can integrate any equipment, from a simple synthesis robot to a complex characterization system. Let's look at how to implement a custom robot interface in Python. You create a custom robot interface class with 3 key methods: init for setting up your robot connection, execute experiment for running a single measurement, and run experiments for processing all proposed candidates. The optimization loop cycles through 4 stages: AI selection using PHYSBO or another algorithm, robot execution of the proposed experiments, result processing back to NIMO format, and updating the candidate list with measured values. In your actual code, you would replace the execute experiment placeholder with your real robot control commands, whether that's controlling a sputtering system, a chemical synthesizer, or any other equipment. Real materials often require optimizing multiple properties simultaneously. For example, you might want to maximize both strength and ductility, or balance energy density with cycle life. This is where multi-objective optimization comes in. The key concept is the Pareto front, the set of solutions where you cannot improve one objective without sacrificing another. On the Pareto front, solution A might have high strength but low ductility, solution C has high ductility but low strength, and solution B represents a balanced compromise. NIMO uses the PTR algorithm, Pareto-based Thompson ranking, to efficiently explore these trade-offs. The final choice among Pareto optimal solutions depends on your specific application requirements. Setting up multi-objective optimization in NIMO is straightforward. In your candidate's data frame, simply add multiple objective columns: Objective 1 for your first property, Objective 2 for your second property, and so on. Initialize these with none values. When calling NIMO, selection, set method to PTR for Pareto-based Thompson ranking, and critically, set num objectives to 2 or more. The numProposals parameter works the same as single objective optimization. NIMO automatically detects the objective columns and optimizes for the Pareto front. The output will be candidates that explore different regions of the trade-off space. In real materials design, you often face constraints. Compositions must sum to 100%, certain element ratios must be maintained for phase stability, and some combinations are simply physically impossible. The key is to pre-filter your candidate space to only include valid compositions. For ternary systems, where x1 plus x2 plus x3 equals 1, you can use a simplex sampling approach. Generate a grid of points within the valid composition triangle, ensuring each combination sums to exactly 1. This gives you, say, 66 valid ternary compositions to optimize over. NIMO will only select from these valid candidates, automatically respecting your constraints. NIMO supports different experimental strategies depending on your throughput capabilities. Sequential mode with numProposals equals 1 gives maximum learning per experiment, as the AI fully updates its model before each selection. This is ideal when experiments are expensive or slow. Batch mode with 3 to 10 proposals balances learning and throughput, letting you run parallel experiments while still benefiting from AI guidance. Large batch mode with 10 or more proposals is designed for high-throughput screening systems that can run many experiments simultaneously. When running batch experiments, use Thompson sampling as your acquisition function. Thompson sampling naturally provides diverse candidates, preventing redundant experiments within the same batch. Real experiments are messy, and NIMO is designed to handle that. When experiments fail, you have 3 options. Mark them with a special value like -999, exclude failed points from the optimization entirely, or queue them for rerunning in the next cycle. For noisy measurements, which are inevitable in real systems, PHYSBO's Gaussian process naturally accounts for measurement noise. You can improve results further by running replicate experiments, averaging measurements, and tracking measurement uncertainty. The key message is to plan for failures and noise from the start. Build your robot interface to handle exceptions gracefully, and don't expect perfect data from real equipment. To continue your NIMO journey, here are the key resources. The NIMO GitHub repository contains the source code and example notebooks. The PHYSBO documentation provides detailed guidance on the underlying Bayesian optimization algorithms. The NIMS website offers research publications and case studies from actual materials discovery projects. For deeper understanding, I recommend our related AI Terakoya series. Bayesian Optimization Introduction for the Mathematical Foundations, Active Learning Introduction for Advanced Experiment Selection Strategies, and High-Throughput Computing Introduction for Scaling Up Computational Workflows. The key, papers by Tamura and colleagues on NIMSOS, and UNO and colleagues on Combo, provide the academic background. Congratulations on completing the NIMO Introduction series. Let's recap what you've learned. You now understand the combat interface for custom robot integration, multi-objective optimization using PTR for Pareto optimal trade-offs, constraint handling through candidate prefiltering, batch versus sequential experimental strategies, and real-world considerations for handling failures and noise. With this knowledge, you can understand closed-loop materials optimization concepts, set up and run NIMO optimizations, choose appropriate AI algorithms for your problems, visualize and analyze optimization results, and extend NIMO for real-world applications. I encourage you to start experimenting with NIMO on your own materials problems. Don't hesitate to explore the advanced features as your needs grow. Thank you for learning with AI Terakoya.